Hi guys, so we're going to run through probability distributions. Now I would recommend I am going to use both calculators today. So I've got the bigger one that's just going to make the binomial distributions a little bit easier, and then I've got the little one that's going to make your NCR values that little bit easier, just because the buttons are a bit fiddly on the graphical calculator. Completely your choice. If you want to stick with one, feel free, but like I say, it is one topic's a little bit easier on one and one's a little bit easier on the other one, so I would recommend both calculators. So probability distributions, you've got a few key facts that I've listed at the top. These are just out the book, but I know some of you haven't got the book, so I've basically typed it up for you. Now, the main thing is that we're talking about ways in which a probability distribution could be asked to be given. Okay, so you've got a few different options. You've got what they call a probability mass function, okay, which means the probability of your function equaling, so having 2 successes, 5 successes, that sort of thing, equals 1/6. So this is, talking about the score when you roll a fair dice. Okay, so probability is a 1/6 given that X, or your outcomes, is to get the numbers 1 to 6 on a dice. Okay, it's one of these two that are likely to come up. This one actually does show up quite often. Okay, which is where you represent your probability in a table, and it literally means, well, what outcomes have you got? You could get the outcome 1, 2, 3, 4, 5, or 6 off a standard fair dice. Okay, probability of each is 1/6. Okay, and now if you get all of these the same, okay, so if all the probabilities are the same, it's known as a discrete uniform distribution, which I put in here. Oh, look, I put it in here. Right, which is in a little bit further down. So you've got, it's known as a discrete uniform distribution. Okay, as always with probability and outcomes of an event have to add up to 1. Okay, so just be careful of that. And then the other one is a diagram. It's not very often used. It's a bit more of a rare thing to show up, but it could come up as draw it in a diagram, in which case you've got your outcomes of the numbers 1 to 6 on the dice. Each one of them have exactly the same probability, so my diagram just shows each one being at exactly the same height. Okay, so those are your 3 options. Like I say, these 2 are more likely to show up. This one is more how a question might be presented. This one is quite often what gets asked as how they want you to give an answer. Okay, so if we look at our first example, we've got 3 fair coins are tossed. We want to write down all the possible outcomes when the 3 coins are tossed. So this is basically like GCSE at this point. Sorry, just got 1 too many things in the way. Okay, that's better. So this first part A, is actually standard. It's just like you'd have at GCSE. So if 3 coins are tossed, just make sure that you follow a pattern. So you could get heads on all of them. I could have 2 heads and a tail, obviously in multiple different orders. Just make sure that you, like I say, are nice and organised about the way that you present it. And then you could have 1 head but 2 tails, again in different options. And then the last one is 3 tails. So you've got 1, 2, 3, 4, 5, 6, 7, 8 outcomes. Okay, and that's it. You've listed all your possible outcomes. That's part A. Part B, we're going to show this with its probabilities, okay, in a table form and then in a probability mass function. Okay, so table form is you've got your outcomes and you've got your probability of that outcome, and our probability is defined as the number of heads that you get. So number of heads, well, you could get 0, you could get 1, you could get 2, or you could get 3, since you're tossing the coin 3 times. Now what you could do is just look back at what you've got here. So the probability of getting no heads at all is just this one, so it's 1 out of 8. The probability of all 3 being heads is just once, so that's 1 out of 8. The probability of getting exactly 1 coin showing a head, you've got 1, 2, 3, so that's 3/8. And then 2 is 1, 2, 3, so that's 3/8 again. And that's your probability distribution function Remember, this just stands for the number of heads from tossing the coin. Okay, part 2, write it as a probability mass function. Now, this is the way you are more likely to see questions actually given in the first place. So you've got the probability of your random variable equaling x, gives us, and our possible outcomes. Okay, now our outcomes is that you could get 1/8, you could get 3/8, and then option as always is to get 0. Okay, in which case probability of getting 1/8 is when x is equal to 0 or 3. Probability of 3/8 is when x equals 1 or 2. And then 0 is otherwise. So, for example, probability of getting 4 heads given that you're only throwing 3 coins means 0 probability of getting 4 heads in 3 coins. And that's it. Hopefully nice and straightforward for the first example. Right, if we look at the second one, you've got a biased 4-sided dice with faces numbered 1 to 4 is rolled. The number on the bottommost face is modelled as a random variable x. Given that the probabilities are in the form k over x, find the value of k. Well, first of all, if you imagine drawing this out in your normal table form, we know that our values that x can take are 1 to 4. So you've got 1, 2, 3, 4. We know the probability of each of these is in the form k over whatever our x is. So k over 1 is obviously just k, k over 2, k over 3, and k over 4. And then remember back to what we said right at the beginning, which you'll have learned since primary school. Probability adds up to 1. Okay, so I know that if I add all these up, they have to add up to 1. So I can say for part A that k plus k over 2, k over 3, and k over 4 has to equal 1. All we're going to do is we're going to make this a little bit easier. I can multiply all the way through by 12, which will eliminate all of my numbers on the bottom there. So I get 12k plus 6 plus 4 plus 3 equals 12. That gives me 12, 22, 25. And so k equals 12 25ths. So you found your value of k. Part B is you're going to give the probability distribution of x in table form. So we're basically going to redraw this table, but actually put our values of k in. Again, spinner can land on 1, 2, 3, or 4. Sorry, 4-sided dice. Seems weird to say 4-sided dice. In which case, probability for this one was just k, so that's just 12 25ths. Probability of landing on 2 was k over 2, so half of this is 6 25ths. A third of it is 4 25ths. And a quarter of it is 3 25ths. And that's it. I've got my probability distribution in table form. Now, part C is we actually want to find these probabilities. So we want to find the probability that our value comes out greater than 2. Well, since these are my only options, if I want the probabilities greater than 2, I want this one or this one. So in other words, I want 4 25ths or 3 25ths. More than one option, probability, you add them together, I get 7 25ths. For the second part, I want the probability that x is between 1 and 4. So in our case, if it's between 1 and 4, it's not actually including either one, which means I'm only looking at 2 and 3. So I've got 6 25ths, add 4 25ths. So I've got 10 25ths, which you can simplify to 2. Sorry, thinking at the same time. Simplify to 2/5. And then the third one, we want the probability that x is greater than 4. Now remember back to the probability mass function we did on the last one. Anything outside of our region obviously can't happen. So we don't have a possibility of getting a number that's bigger than 4. In which case, probability that x is greater than 4 is just 0. Okay, again, hopefully that makes a bit of sense. Feel free to listen back through at any point if you're getting a little bit stuck. And then example 3, what I've got is this spinner. Now, I did forget, you know, there's always something somewhere to label this. Hopefully, if you've printed it in colour, which I didn't actually get round to, those 2 are red, these 3 are blue. Okay, so that's my spinner. It says the spinner is spun until it lands on red or has been spun 4 times. So just be careful not to be tripped up by this sort of question. Find the probability distribution of the random variable, and they're calling it S now instead of X, the number of times the spinner is spun. So we're only going as far as 4 times. So basically we need to find our probabilities. We want to find either when S is equal to 1, okay, so if it's spun once, and we're obviously aiming for landing on red, red would be 2 out of the 5 sections, so that one is just 2/5. Since this is essentially the same as me saying what's the probability of spinning a red. Okay, if I look at the next one, if I want the probability that it took 2 spins to get to land on red, that means I must have landed on blue the first time and then red the second time. So blue would be 3/5. Red is 2/5, so it's 3/5 the first time, 2/5 the second time. Think back to tree diagrams at GCSE, you just multiply along the branches. So 3 times 2 is 6, 5 times 5 is 25. So that's essentially from GCSE us saying that we landed on blue first and then red. You obviously don't need to write this bit down, but it might help you see where we're getting the answers from. So for the probability that it took 3 spins to reach red, again, that means I must have landed on blue the first time, blue the second time, and then red the third time. Okay, in which case I've got 3, 9, 18 over and then 125. So that was just probability blue the first time, blue the second time, and red the third time. Now be very, very careful of this. Do not follow this pattern for the 4th one, because remember, we're only spinning a total of 4 times, okay, because we're looking for red or to have spun it 4 times. So the probability of spinning 4 times, or needing to spin the spinner 4 times, must be 1 minus and the other 3 options that you could have had. So 2/5, 6/25, and 18 over 125, which if we chuck into a calculator, we're going to get 27 125. Okay, and we want to show this as a distribution function, so we're going to go with the table method again. You are obviously looking at it landing on first spin, second spin, third spin, 4th spin, and you're just going to write your probabilities in. So first one was 2/5, then you've got 6/25, 18 over 125, and 27 over 125. And that's it. You've got your probability function for this spinner. Okay, so that leads you up to exercise 6A in the textbook. Okay, have a go at exercise 6A. Make sure that you're okay with it all. Obviously, keep an eye on your answers. Any problems, let me know. And then come back to the video. We're going to move on to binomial distribution. Okay, so binomial distribution, you'll recognise a little bit more. It's just putting a use to binomial expansion. Okay, now these key facts here, okay, which again I've typed up, are the facts which are 99% of the time asked for in an exam. Okay, they will always give you, for example, a type of experiment that's happening and want you to say whether it could be a binomial distribution and to give reasons why. Now, any type of question like that, to explain a binomial distribution, you must give reasons for all 4. Okay, so you have to show that it's got a fixed number of trials. Okay, you have to say that there's only 2 possible outcomes, success and failure. So it could be landing on or rolling a 6 is success. Rolling any other number on a normal dice would be failure. Heads on a coin would be success. Tails would be failure. Passing an exam, failing an exam, winning a football match, losing a football match. You'd have to state that they're not including drawing in the match. You can either win or lose. Okay, so it's anyone like that. Left-handed, right-handed comes up quite often as well. A fixed probability of success, so the chance of that happening is always fixed. So on a standard dice, the chance of you rolling a 6 is 1/6. The trials are independent of each other. Obviously, rolling a dice and then rolling it a second time, the second one's not affected by the first one. You're looking at an independent event, okay? And then probability always follows the same setup as your binomial expansion. So you've got your NCR number. Okay, I prefer writing it as the NCR number. You can write it like this if you like. That's completely up to you. And then you've got however many successes you've got. Since probability adds up to 1, P obviously stands for success. So 1 takeaway P must be failure. So if you think N is how many trials you've got, R is however many successes you're looking for. So if you wanted 5 successes, you'd do success to the power of 5, failure to the power of 15, for example, if there was 20 trials. Okay, so it's success and then failure. So if we've got the random variable X being distributed binomially, okay, you've got N is the number of successes, P is your probability of failure. Sorry, probability of success. We want the probability that X equals 2. So the first one, probability that X equals 2, just means that you've got 12 trials. You want 2 successes. So you want 12C2. You then want probability of success is 1/6. And we're looking for 2 successes. So if you've got out of 12 trials, 2 successes, failure must be 5/6 because probability has to add up to 1. And because there's 12 trials, if 2 are successes, 10 must be failures. And all you're going to do is literally chuck that in a calculator and write down exactly what your calculator gives you. Okay, and this one is the one that's much easier on a standard calculator. You've got shift and it's right there, NCR. Okay, it is the same on the slightly older calculators as well. You can use the graphical calculators, but you end up going through the catalogues, searching for your NCR button. It's a lot of messing about. I would personally just recommend using 2 calculators. Okay, on the next one, we want the probability that X equals 9. So you're going to follow the same idea. Still 12 trials. You want 9 successes. Probability of success is 1/6, and we want 9 of them. So failure would be 5/6. And again, if there's 12 trials, 9 successes means there had to have been 3 failures. And again, you're just going to chuck that straight into a calculator, write down your number. It does quite often come out in standard form, so just recap your standard form if you're not quite confident with it. Okay, this one obviously comes out as 1.26 times 10 to the minus 5. It does sometimes say e to the minus 5 on the newer calculators rather than times 10. Okay, now for the third one, you've got probability that X is less than or equal to 1. Well, if you think about that logically, that means either you've got the probability of 0 successes or the probability of 1 success. So that means all I want to do whenever we say or, remember with probability we're adding. So you want to find the probability of 0 plus the probability of 1. Now I am going to show you this written all out, and then I'm just going to show you how to cheat with the calculator. But probability that X is 0, you've got 12C0, 1/6 to the power of 0, 5/6 to the power of 12, and then you're adding on 12C1, 1/6 to the power of 1, 5/6 to the power of 11. You can, by all means, type all of that into a calculator, work out what you get 0.381. Now, what you can do, which we're actually going to learn in a minute, but we might as well start now, is on the new graphical calculators, you're just going to click menu. We're going to put it on statistics, so number 2. Ignore all the numbers. I honestly forgot how to delete them. So if you go on to distributions and we want a binomial distribution, you'll have a few different options. Don't worry about the inverse one, IMV, inverse binomial. We haven't got around to that. That'll be second year stuff. You've got a binomial probability, so that's finding an exact amount, like finding the probability that equals 9. And then you've got a binomial cumulative distribution, so that's adding up to a certain value. So cumulative would mean everything up to and including 1, for example. So we're going to do a cumulative distribution. It's always variable at this point. Lower obviously starts at 0 because we are looking at an exact number of values. You can't go into negatives. So we want to start at 0. Our upper value is 1. And then, number of trials is, we were looking at 12 trials, so that's fine. And then probability of success is 1/6. Okay, in which case you get 0.381. You can see I got the exact same value as I got by typing it into the other calculator. This one just gets you there a little bit faster. Okay, next one, we've got the probability that a randomly chosen member of a reading group is left-handed is 0.15. So you've got our p-value. You've got a random sample of 20 members. There's our n value. Suggest a suitable model for the random variable x, the number of members in the group who are left-handed. So if we're saying x is left-handed people, then you've got a binomial distribution, because you can say x is distributed binomially. You've got 20 trials, and success is finding a left-handed person, which is a probability of 0.15. But remember, it says you have to justify your choice for your suitable model. And whenever we're talking about binomial, remember there's 4 key things that you are going to talk about every single time. Okay, binomial, so it's got that 2 parts to it. So you've got 2 outcomes. Okay, 2 outcomes are either that you are left-handed or right-handed. Okay, second one, we want to talk about a fixed number of trials. In other words, we are testing a certain number of people. They're going to say 20 members. Okay, we're only looking at those exact 20. You then want a fixed probability of success. Now, it tells you the probability of picking a left-handed person is 0.15. And then our last one is talking about that it has to be independent. So you're just going to put, you're assuming each member in the sample is independent. Okay, so choosing one person, you're not going to pick another one. Right, so part B. Use your model to calculate the probability that exactly 7 members are left-handed. So you want the probability that x equals 7. So like I said, you can use your NCR value. So you've got 20 trials, 7 successes. You want success as 0.15 to the power of 7. Failure as then would be 0.85, since it has to add up to one whole one. And there must be 13 failures if you had 7 successes. So you can just type that into the smaller calculator. So don't turn it off. You've got 20C7, 0.175 to the power of 7, and then 0.85 to the power of 13 is going to give us 0.0160 to 3 significant figures. Okay, but again, you can, if you want to, go back to this calculator. Remember, you put your menu on 2 for statistics. You want your distribution. We want binomial. This one, we actually want the probability distribution because we want the exact value. Okay, now the value of x we're looking for is 7. The number of trials we have is 20. And our chance of success is 0.15. Type it in a calculator and you get exactly the same value as what I found on the other calculator. So the choice is completely up to you whether you want to use this or whether you want to type it all in. both will work absolutely fine and both get you marks in the exam. Okay, and then part 2, you've got fewer than 2 of the members in the sample are left-handed. So you want the probability that X is less than 2. Now, because this is discrete variables, you can't have, for example, 1.5 people. So in other words, the probability that X is less than 2 is actually the same as the probability of X being less than or equal to 1. So if you want to go for this method, you'd need the probability that X is 0 plus the probability that X is 1. If you want to go for the calculator method, you want the probability that X is less than or equal to 1. So we're going to go back to our distribution. This time on binomial, we want the cumulative distribution, so B, C, D. Obviously, it's 0 as the lowest. We only want to go up to 1 again. Number of trials is 20. Probability of success is 0.15. You're going to get 0.176 to 3 significant figures, which was considerably faster than having to type this in with 0 and with 1 and add them up without making a mistake anywhere. Okay, you're now going to have a go at exercise 6B out the textbook. Okay, and then I am going to keep all of this on one video, so pause it at that point, come back to us when you get onto the next one. We're going to look at cumulative probabilities, which we have already kind of touched on. Okay, we're just going to do this a little bit more in detail. There is only 2 examples with this one, so it shouldn't take us long. We are going to stick with using the calculator with all of these as well. So we've got a distribution. There's 20 trials. The chance of success is 0.4, so this is our n value. This one is our p-value. Okay, we want for the first one the probability that X is less than or equal to 7. So that means we're going back to this. Again, I'm going to go from distribution, binomial, cumulative. We want to go everything from 0 to 7. So 0 to 7. Number of trials is still 20. Why it does that sometimes, not other times. And then success is 0.4, in which case what I've ended up with is 0.416. Okay, so nice and hopefully straightforward for the first one. Second one, probability that X is less than 6. Now remember, again, like we said, it's discrete, so you're looking at 5 successes, 6 successes, 7 successes, and so on. In other words, that is the same as the probability that X is less than or equal to 5. Now the reason we want a less than or equal to is so that we can use the cumulative distribution function. I can come back to this and I can just change the 7 to a 5, in which case I get a value of 0.126 to 3 significant figures. Okay, so again, hopefully first 2 very straightforward. Now the probability that X is greater than or equal to 15. Now I will show you this. It depends on which calculator you are using. Okay, if you think about this as this is all of my probability, all of my successes, I am going from 0 successes to 20 successes. So if I want 15, I'm looking along 3/4 of the way, there's my 15 successes. I actually want this bit here, which means if you are using the smaller calculator, it doesn't do cumulative binomial in the same way the other one does. Okay, for the smaller calculator, you would have to remember that all the way along has to add up to 1. So if you want this bit here, the cumulative distribution on the smaller calculator, you will find this value here, in which case what you'd actually need to do is 1 minus the probability that X is less than or equal to 14. Okay, because if you find from 0 to 14 and then do 1 minus, you've got 15 and above. Okay, everything's still being discrete. Or if you're on the bigger calculators, the graphical ones, you just put your lower value as 15 and your upper as 20, since there's only 20 trials. So these calculators do make it a little bit of a cheat. Lower value, like I say, you want at least 15. There's only 20 trials altogether, so you just put it up to 20. Number of trials is 20, probability is 0.4. And like I say, rather than times 10, it does say E. So this would be a final value of 0.00161 to 3 significant figures. Okay, but like I say, you can use the smaller calculator. It's absolutely fine. It just doesn't quite work exactly the same way. It can find the probability that x is less than or equal to 14. You then have to do 1 minus that answer, which just makes it that little bit fiddlier. The graphical ones just make it that little bit easier. Right, second part. You've got a spinner is designed so that the probability that it lands on red is 0.3. Jane has 12 spins. Find the probability that she obtains no more than 2 reds. So for part A, no more than 2 is the probability that x obviously has to be less than or equal to 2. In which case you can chuck it back in your calculator. You've got 0 to 2. We're talking about 12 trials, and we're talking about probability of success as 0.3. Chuck it in your calculator, you get 0.253 to 3 significant figures. Okay, for part B, you want at least 5 reds, so you want the probability that x is greater than or equal to 5. Remember, cumulative starts at 0 and goes up to the value you're looking for. Okay, so if you're using the smaller calculator, you're going to do 1 minus the probability that x is less than or equal to 4. If you're using the bigger calculator, which we are, you're just going to do it so much easier. You're just going to put your lower value as 5 because you want at least 5. There was a total of 12 spins, so that's how many trials you've got. Probability is 0.3. You get 0.276, which is why the bigger calculators make it that little bit easier. But like I say, there's always little bonuses to each one, so 2 calculators in the exam will make life a little bit easier. For part C, Jane decides to use this spinner for a class competition. She wants the probability of winning a prize to be less than 0.05. Each member of the class will have 12 spins and the number of reds will be recorded. Find how many reds are needed to win a prize. So what you need to do is we're basically looking for the probability that x is less than or equal to some value. Okay, has to be smaller than 0.05. Okay, because we're looking for the probability of success, so we're looking for it to be less than 0.05. This is kind of like a trial and error thing. You're just going to try typing some numbers in. So if you test, for example, the probability that x is less than or equal to 5, again, you're just going to chuck it into your calculator. So I've got lower as 0, upper as 5. It's still 12 trials because she's still spinning it 12 times. It's still the same spinner, so probability is still 0.3. You get 0.882. Now obviously, because we're looking for there to be how many spins it would take to win, we're looking the other side. So we're basically saying that this value, we're looking for a value that comes up greater than 0.95. So if I try 6 trials, for 6 trials you get 0.961. So that's where our value is getting greater than what we had. So in other words, the probability that x is greater than or equal to 7, so the probability of getting 7, what we're looking at, 7 reds on our spinner, has to be 1 minus the value we've just worked out, which is 0.03. So that's our chance of getting 7 or more spinners, and we want that probability to be less than 0.05. Therefore, 7 or more reds will win the prize. Okay, so it's a little bit more complicated thinking about what's going on there, but you're looking for how many reds would you need to get where the probability of you getting that value is actually less than 0.05. Okay, so all you're going to do is have a go at exercise 6C. Okay, and that is all of the statistics chapter, which I think was chapter 6. Actually, was obviously chapter 6. Okay.